Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started.
Ever tried balancing a pen on your fingertip? It's tricky, right?
Yeah, definitely takes focus.
Now imagine, like half a dozen pens, all doing that, all reacting differently. That's kind of what flying a drone feels like, this constant juggling act.
That's a really good analogy, a whole set of balances happening at once.
Exactly. And today, we're taking a deep dive into those core principles, the things that don't just let drones fly, but let them move with, precision and stability.
Right. And the practice questions you sent over, they really hit the key areas. We've got the basic movements, pitch, roll, and yaw. Then there's the Bernoulli Principle, how lift actually happens, load factors, G-forces during maneuvers.
The strain on the drone itself.
Exactly. Propeller power and efficiency, the importance of the center of gravity, that balance point. And then the big picture, aerodynamic stability, tying it all together.
Perfect. And our goal isn't just to, list the answers. We want to really unpack these ideas, understand why they matter for anyone flying a drone or even just interested in them.
Connect the dots between these concepts, see how they all interact.
Yeah, hopefully have a few aha moments along the way. All right, let's dive in. Starting with the basics. Pitch, roll, and yaw. The drone's language of movement.
Okay, so think of these as the drone's main ways of changing its orientation. Pitch, that's the nose tipping up or down, movement around the lateral axis.
Like nodding yes.
Kind of, yeah. Then roll is the side-to-side tilt around the longitudinal axis, nose to tail. Think of an airplane banking.
Tilting left or right.
Right. And yaw is the rotation, spinning left or right while hovering around the vertical axis, like shaking your head no, but the drone stays mostly in one spot horizontally.
Got it. And the control mechanisms are pretty clever based on the material. Pitch seems to be about varying front and rear motor speeds. Faster rear makes the nose dip.
That's generally how it works, yes. Creates that tilting force. And yaw often involves speeding up motors on opposite corners, creating that rotational force.
Okay. And roll. Just varying the speeds on the left versus the right side motors.
Exactly. It's this constant, subtle adjustment of motor speeds to manage these three axes. Like your fingers constantly adjusting for those pens.
What's really interesting is how they have to work together.
Yeah.
The sources mentioned coordinated turns using yaw and roll. What happens if you don't coordinate?
Well, if you just roll hard without adding some yaw, the drone can lose altitude or sort of slip sideways. It's a bit like turning a bike. You lean, that's the roll, but you also steer slightly, the yaw, to keep it smooth and controlled.
Oh, okay, that makes sense. And for anyone doing drone video, understanding yaw seems absolutely critical for those smooth panning shots.
Oh, definitely. It lets you rotate the camera view without having to physically fly the drone sideways. Much smoother results.
But the questions also hinted at problems. What can go wrong with pitch, roll, or yaw?
Well, uncontrolled yaw, for instance. If the drone starts spinning unexpectedly, that could be an issue with one motor not putting out enough thrust, an imbalance, or maybe a compass calibration error, so it loses its sense of direction. And the sources also caution about pitch, especially near the ground, aggressively pitching forward when you're low. Well, that can lead to a quick meeting with the terrain.
Yeah, ouch. Okay, so that's movement. Now, how does it actually get off the ground? Let's talk Bernoulli's Principle. Sounds like something from physics class.
It absolutely is a fundamental concept in fluid dynamics. Basically, Bernoulli's Principle states that faster moving air has lower pressure.
Faster air, lower pressure. Okay.
So if you can make air move faster over one surface compared to another, you create a pressure difference.
And that's lift. How does a propeller do that?
It's all about the shape of the propeller blade. It's an airfoil, just like an airplane wing, but, smaller and spinning. The top surface is curved.
Right.
So the air flowing over the top has to travel a longer path than the air underneath in the same amount of time. To cover more distance, it has to speed up.
Faster air on top means lower pressure on top.
Exactly. And you have higher pressure underneath pushing up. That pressure difference is what generates lift. The propellers are essentially spinning wings.
Right. Okay, that clicks. And the angle they hit the air, the angle of attack, that matters too.
Very much so. Increasing the angle of attack generally increases lift because it forces the air to curve even more. But only up to a point.
What happens then?
If the angle gets too steep, the airflow can detach from the top surface. It becomes turbulent and you lose lift suddenly. That's a stall. It's a critical balance.
So spinning the props faster, increasing RPM, that makes the drone go up because it increases that airspeed difference.
Precisely. Faster spin, more airflow, greater pressure difference, more lift. When that total lift from all props equals the drone's weight, it hovers. When lift exceeds weight, it climbs.
It's amazing that relatively small blades can generate enough force.
It is, though the sources do rightly point out Bernoulli isn't the whole story for lift.
What else is involved?
Well, there's also Newton's third law. For every action, there's an equal and opposite reaction. The propellers are actively pushing air downwards.
And the reaction is the air pushing the drone upwards.
Exactly. So it's really a combination of that pressure difference from Bernoulli and this direct action-reaction force that gets the drone flying.
Fascinating. Okay, so we're up, we're moving. But what about the stress? Load factors and G-forces. This sounds more like fighter jets.
Well, the principles apply, just on a different scale. Load factor measures the total force on the drone's structure compared to its normal weight at rest. We usually talk about it in Gs. 1G is just normal gravity.
So if a drone makes a sharp turn, it experiences more than 1G, like being pushed into your seat on a roller coaster.
That's the perfect analogy. You feel heavier, the drone feels heavier too. The practice questions note that a 60-degree banked turn roughly doubles the load factor to 2G.
Wow, so a 2-kilogram drone effectively puts a 4-kilogram load on its arms and frame.
Exactly. And if it hits 3G in a really aggressive maneuver, that's a 6-kilo effective load.
That sounds like a lot of stress. Why is understanding this so important for pilots?
It's all about avoiding structural failure. Pushing the drone too hard, exceeding those G limits, can damage the arms, the motor mounts, maybe crack the body.
Or mess up the camera gimbal?
Absolutely. Gimbals are sensitive, so knowing the limits helps prevent damage and maintain control. It's not just about the motors having enough power.
So the advice is smoother, wider turns.
Generally, yes. That keeps the G load down. But it also explains why you often need to increase throttle in a steep turn.
Right. Why is that?
Because when you bank, some of that vertical lift from the props is now being used to pull the drone sideways into the turn. To stop yourself from descending, you need more overall thrust to compensate for the vertical component you've redirected.
Makes sense.
Yeah.
The sources also mentioned rapid pullouts being tough.
Yeah, if you dive and then pull up sharply, the G-forces can spike really high. And if the motors can't instantly provide enough lift to counteract both gravity and that high G load, the drone could actually lose altitude for a moment, even while pulling Gs.
Counterintuitive, but logical. Okay, so propellers create the thrust to handle all this. Let's talk about them. Power, efficiency. Thrust is just the upward force they generate, right? Newton's third law, again, pushing air down.
Correct. And generally, faster spinning, higher RPM means more air moved, so more thrust.
But it's not just about raw speed. Efficiency matters, too. What kills efficiency?
Oh, several things. Damaged props are a big one. Even small nicks disrupt airflow. Air density is huge, too.
Like at high altitudes.
Exactly. Thinner air means the props have less stuff to push against. Same RPM gives less thrust. Hot weather does the same thing. Air is less dense.
The questions mention high-pitch props. What's the deal there? Pitch is like how far it moves forward in one spin.
Theoretically, yes. Higher pitch props can bite into the air more aggressively, potentially giving more speed or thrust for a given RPM, but they usually need more power to spin and can be less efficient just hovering at low RPMs.
So it's a trade-off, speed versus hover efficiency.
Pretty much. Blade length also matters. Longer blades move more air, potentially more thrust, but again need more motor power. And the actual shape, the airfoil design, is super important for efficiency.
And balance seems crucial. Why?
An unbalanced prop causes vibrations. That wastes energy, reduces efficiency, stresses the motor bearings, and can even cause weird jello effects in your video. Always best to replace props in pairs or sets if one gets damaged.
And putting them on backwards is a definite no-no.
Oh, absolutely. They'll push air the wrong way. Instant instability. Maybe even a flip-on takeoff.
Yikes. What about prop wash?
That's just the turbulent air pushed downwards. You can feel it. It can sometimes affect stability if you're flying very close to the ground or another surface.
And if you want more thrust without bigger motors, Higher pitch or larger diameter props?
Those are the main options, yes, assuming the motors can handle the extra load.
Yeah.
And blade count. More blades can make it quieter, often looks cool, but usually slightly less efficient than a well-designed two-blade prop of the same overall size. Another trade-off.
Okay, lots going on with props. We've got thrust, we're managing G's. But what keeps the drone stable? What stops it just tumbling? That brings us to the center of gravity, the CG.
Ah, yes, the balance point. The CG is simply the point where the drone's weight is perfectly balanced in all directions. Getting this right is, well, fundamental for stable flight.
How do you actually check it? The sources mentioned lifting it.
Yeah, a common way is to carefully pick it up by the motor arms or designated points. If it hangs level, the CG is likely centered. If one end or side dips down, it's off balance.
And if it's off, what happens in the air?
It'll tend to drift or tilt. If the CG is too far forward, the drone will constantly want to pitch nose down and drift forward. Too far back, it might pitch up, especially on takeoff.
I bet adding a camera or a sensor really throws it off.
Oh, absolutely. Any payload changes the weight distribution. You have to recheck the CG after adding or moving anything significant. Often you can slide the battery slightly forward or backward to compensate and get it balanced again.
Does side-to-side imbalance matter as much as front-to-back?
It definitely matters. Left-right imbalance primarily affects the roll axis. The drone will want to constantly bank to the heavier side. Ideally, you want the CG centered, usually right below the plane where the propellers are.
What are the signs in flight that your CG might be off?
Uneven climbing, maybe one side lifts faster than the other, or just that constant feeling that you're fighting the controls, always needing to make small corrections just to keep it hovering level.
And the flight controller can struggle with a bad CG too.
Yeah, even though its job is to stabilize, if the imbalance is too great, the controller has to work overtime. This can lead to jerky movements, oscillations, maybe even overheating motors as it tries desperately to compensate. And it's worth recalibrating sensors after a big CG shift, just to be sure the flight controller has the right baseline.
Okay, so balanced CG is step one.
Yeah.
Then we have aerodynamic stability overall. What does that encompass?
It's the drone's inherent tendency to fly straight and level, and its ability to return to that state if it gets disturbed, say by a gust of wind. This relies heavily on the sensors.
The gyroscopes and accelerometers.
Exactly. Gyros detect rotation, how fast it's pitching, rolling, or yawing. Accelerometers detect linear movement and help figure out its orientation relative to gravity. The flight controller takes all this data and makes lightning-fast adjustments to motor speeds to keep it stable or follow commands.
The questions mention static versus dynamic stability. What's the difference there?
Okay, so static stability is the initial tendency to return to equilibrium. Nudge it, does it immediately try to go back? Think of a ball in a bowl it wants to return to the bottom. That's statically stable.
Got it. And dynamic.
Dynamic stability is how it returns. Does it settle back smoothly, or does it overshoot and oscillate back and forth? A dynamically stable drone dampens those oscillations quickly. An unstable one might oscillate more and more wildly.
What kind of things make a drone unstable then, besides bad CG?
Well, many things we've touched on. Uneven motor thrust, maybe a failing motor, an unbalanced or damaged prop, incorrect prop installation, even sensor issues. If the gyro or accelerometer isn't calibrated right, the flight controller gets bad information.
Does GPS help with stability?
It can, indirectly. It helps the drone hold its position, providing a reference point, which contributes to overall stable operation, especially in hover. But the core aerodynamic stability comes from the sensors and the flight controller's constant work.
What would I actually see if my drone was unstable?
You might see wobbles, oscillations, maybe a constant drift even in calm air. Uncommanded rolling or pitching. In severe cases, like after a motor failure, it could start spinning uncontrollably. Even just adding a heavy camera on the nose can mess with pitch stability if the CG isn't rebalanced.
And instability probably hits battery life too.
For sure. The flight controller and motors are working much harder, constantly making corrections. That burns more power.
Right. Wow. Okay. We've covered a lot of ground, from basic movements to the physics of lift and the complexities of balance and stability. Let's try and wrap it all up.
Yeah, it's all connected, isn't it? The pitch, roll, and yaw movements are only possible because the propellers generate thrust.
Which relies on principles like Bernoulli's and Newton's laws.
Right. And while doing all that, the drone structure has to withstand G-forces during maneuvers.
And none of it works reliably without being properly balanced around that crucial center of gravity.
Which is the foundation for overall aerodynamic stability, managed by the flight controller and sensors. It really is a system.
It really is. And understanding these pieces isn't just, academic. It helps you get a feel for how the drone actually flies, how it interacts with the air.
Exactly. Which leads to being a safer pilot, flying more efficiently, and probably getting more enjoyment out of it, too.
It makes you think, too, how just changing one thing like adding a slightly heavier camera or flying on a hotter day can ripple through and affect everything else. The CG shifts, maybe prop efficiency drops a bit.
The stability might change, you might need different control inputs. It forces you to consider, okay, what adjustments do I need to make now to keep everything in balance?
That's a really important takeaway. Well, keep exploring these ideas, keep learning, and definitely happy flying.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.